Hi, my name's Lindsay. I'm a professor in the CSE department, and Peter asked me to fill in for him today because he couldn't be here. He's fine. Nothing terrible happened to him. He's just at a conference. So Peter asked me to fill in, and it's kind of too bad that he wasn't able to lecture on Wednesday because he was going to lecture about fault tolerance, and that's actually very relevant to what I'm going to talk to you about today. But I'm hoping to introduce some of the ideas, and then some of those ideas will come up quite a bit, I think, in the next 2 weeks while you talk about fault tolerance in this class. Today we're going to be talking about replication, which is very closely tied to this topic of fault tolerance. So to fill in a little bit more background, I guess maybe some of you don't know who I am. So my name's Lindsay Cooper. I just joined UCSC this year, so none of you have ever taken a class from me. But my office is almost right next to Peter's, so you might have seen me if you come to office hours or something. And this is kind of a practice run for me because I'm going to be teaching a version of this class in the spring. So I suppose if anybody drops this class and then decides to take it again in the spring, then you'll see me again. Also, I've been sitting in. So if you've seen me, I've tried to be a fly on the wall in the lectures, but sometimes I kind of open my mouth anyway. So I've been sitting in because Peter's kind of owned this class for the last few years. In fact, he's been the only person who's taught this class I think since 2015 or 16. So, and as you know, it's a very engaging lecture, right? So I'm trying to steal all of his teaching techniques so that I can use them in the spring. So today is kind of a practice run for that, so we'll see how it goes. So today we're going to talk about replication. And so this is a topic that's kind of been touched upon very briefly so far in this course, but it hasn't really been discussed in any detail. So just to throw it out there, if I say the word replication or replicas in the context of distributed systems, what am I talking about? Anyone? Yeah.
Redundancy for data.
Redundant data. Okay, so the thing that I'm replicating is data. All right. Well, as we've talked about, when we talk about a process, so here's a process, say some events on it. One thing that we've discussed a little bit in this class already is this process with these events. This is kind of, when we talk about a series of events, that's kind of equivalent to talking about a state, right? Because this series of events leads to some state. So when you say replication of data, data is like state. So we could replicate this thing and have another copy of it. Why would we want to do this? Sure, go ahead.
Failover, redundancy, backup, network partitions.
Yeah, what if one of these dies, right? It's awfully convenient to have in your back pocket another copy of the process if one of them dies. So let's give them names. So if R1 dies, then it would be awfully convenient if we had an R2 that had exactly the same state with exactly the same event. So reasons for replication. That's the number one reason for replication. Can anybody think of another reason why we want to do replication? Yeah?
Increase the scale of the process. Knowing how to handle a certain number of events, then per unit time, then making another copy of that process.
Increase the scale. So why would we not want all of our requests to go to one of these processes?
Assuming you're not holding both of those in the same location, one can be on one spot at a time, or one can be another, and you can have the people that are closest to that specific process accessing the data.
There you go, yeah. So let's say locality is another reason to do replication. If I'm in Sunnyvale, that's where I live, and one of these replicas is in Santa Cruz, and one of them is in Tokyo, which one does it make more sense for me to hit?
Tokyo. Understandable. At the on where you.
Probably makes more sense for me to hit the one in Santa Cruz. Hopefully that one's available. Now, if it's not available, maybe it died, then I have the other one that I can fail over to. But locality is another important reason for replication, even leaving aside this fault tolerance thing. So replication addresses these issues of fault tolerance and locality. But I like to say, so replication is much like alcohol. It's the solution to and cause of all of life's problems. So what are some of the problems that come up now that we have these two replicas? Now what do we have to deal with? We have to keep them consistent. So this class is basically about how do we do that. And in fact, this class is not just about that, but about what do we do once we've reached this situation where they're not consistent. How do we address that? So to expand this picture a little bit to one that you might have seen already, let's put a couple more processes on here. Let's call this C1. So this is, let's call it client 1. We can pretend this is my laptop. And say client 1 has some event. Maybe it's writing to the, let's say this is event A, or write A. And then we have a client 2, maybe it's my phone. And it's writing B. So this is a picture that's actually been on the board a couple of times before in this class. What is this reminding you of?
Total order anomaly.
So what's the issue going on here? Is what kind of what property is being violated here? Is this a FIFO violation? Total order, right. So just to recap, so why is this not a FIFO violation? Right, yeah. There's nobody who's sending, there's no process that's sending 2 messages to another process, right? So this here, this is ending up, A, then B, and this is ending up B, then A. That's not a FIFO violation. So if we're just enforcing FIFO, this could still happen. Is it a causality violation? That's right, yeah. So A and B are not causally related. So this isn't a causality violation either. We could add vector timestamps on here to prove that, but we don't have to. We can see just by looking at it that it's not a causality violation. And as you said, it's a different kind of violation. It's a total order violation. But this situation is actually pretty normal. And the reason for that is that total order is kind of a pain to enforce. You can't do it with vector clocks, right? Because vector clocks enforce causal consistency, but they don't enforce this total order consistency. So a lot of systems just don't enforce total order consistency. So what would you do if you wanted no total order violations? Let's assume that, I guess in last week we talked a little bit about how would you avoid these sorts of total order violations, and people gave examples of how to implement a protocol that would avoid these total order violations. But it was really involved, right? It would involve something like, well, the sender has to multicast to everybody and they all acknowledge it, and then they multicast their acknowledgement. And that's really hard. And you get into trouble, especially if one of the processes involved crashes. So let's just say that that's off the table and we cannot enforce this total order property. It might just not be practical to enforce that sort of thing. So what do we do? Like when we get into this situation where R1 and R2 disagree, does anybody have an idea about how we fix it? How do we decide what to do? Go ahead. Just shout it out.
One naive solution is just say one of these is the authority and it's right, and the others are wrong.
Sure, okay. So yeah, that reminds me a little bit about how in the Lamport paper, remember how we picked a kind of arbitrary ordering of all the processes? And that was how you turned the partial order of causality into a total order. So this would be kind of like that. Let's say you could just decide, well, R1 is the authority. And indeed, this is what some approaches do. They just say, this one's going to be the one that's right. And everybody else is going to have to correct themselves to what that is. Yeah, go ahead.
You
could also use locks, so you like only allow one specific access to this resource, and then enforce some kind of synchronization of the replicas between requests.
So that sounds like, how would you avoid this happening in the first place? So, which is a good approach, right, if you have the resources to be able to do that. And indeed, you could probably enforce that, in the absence of certain kinds of failures. But let's say that that ship has already sailed, you're already in this situation where these two replicas disagree. So now you have to decide what to do. So the proposal that was already made was just pick one and just arbitrarily declare that that one's correct. And that could work, but it seems kind of arbitrary. Yeah, go ahead.
Could you just take the one that's like updated last, and then if they happen at the same time, then just fall back to like choose a random one last.
Yeah, so this is indeed what some systems do, right? They try to pick the one that has the most recent real-time timestamp. But that's often a no-go, right? Because different systems' clocks disagree, and so that can be really hard to do. Yeah.
Why don't you have R1 and R2 synchronize at certain points in time, and each synchronization has a timestamp associated with it. And so suppose if C2 were to then ask a resource, which is after that timestamp, they would then have to synchronize before they would return that. If it's anything before that timestamp, clearly at that point in time, those resources have been synchronized. So there's consistency. The only thing is that there's going to be a certain interval between which there is no consensus between the two replicas.
Yeah.
And if you request a resource which is part of that interval, you could then force a synchronization and then the resource.
Yeah, so I like your suggestion because it involves R1 and R2 kind of proactively talking to each other before anybody asks. So that's sometimes called anti-entropy, where you have these replicas talking to each other and checking, hey, are you the same as me? Are you the same as me? But it still gets back to that problem of the timestamps. Where do those timestamps come from? Yeah, go ahead.
So someone mentioned to the reader. So if the reader goes down, then what next?
Exactly, yeah. So if you pick somebody and you decide this is the anointed process that's always right, now you're in trouble if that process dies. So this turns out, in general, this is a really hard problem. Yeah, go ahead.
You could hash both the datas, and whichever one's smaller could be the first one.
You could hash them and whichever one's smaller. So do you mean hash the actual contents of the updates A, and B? Okay, I like what you're getting at here, because this is what you're getting at is what we're going to have to talk about. So we'll come back to that. Yeah, go ahead. Sorry, go ahead.
Kind of arbitrary, but if there's process IDs, you could just pick smaller, larger ones.
Right, yeah, so that gets back to that choice that Lamport made to turn the partial order into a total order. So yeah, you could do that, but it's kind of arbitrary. All right, does anybody have a suggestion that doesn't involve like picking a winner of all the processes, or, yeah, go ahead.
You could also just save the state of the processes, and whenever there's a conflict in synchronization, it's returned to the previous state for both of them.
Yeah, okay, so have some previous time where they agreed, and then if you discover that they disagree, you can kind of roll back. Then you get into trouble, because what if you lose all these rights? So, yeah, so in general, this is a really hard problem. So the Lamport total ordering processes are numbered, and we pick the lowest number and let that be the winner. That could work, but it's kind of arbitrary. Using physical timestamps is another approach, but it's kind of a no-go because of clock skew and so forth. So what I'm going to propose is a different idea, and this maybe gets a little bit into what you were talking about, which is we want to look at the actual content of these messages that have arrived here, these messages A and B, and use the content of the messages to decide what to do. So I'm not talking about the vector clocks that might be on these messages as we send them. I'm talking about the actual payload of the messages. And so I think in his last lecture, I guess on Monday, Peter mentioned how we don't care about content of messages in this course, and that will often be true, but today we actually do care about content of messages. So when I say application-specific conflict resolution there, when I say application-specific, what I mean is caring about the particular content of messages. So instead of just, and so in order to talk about the content, let's make this a little bit more specific. Instead of just talking about these generic A and B, let's suppose that we actually know what these events are doing, and let's try to use that information to see if it gives us any insight into what to do to solve this dilemma. So let's turn this into a really, really specific example. So let's say that this thing that's being replicated here is a shopping cart. And these two events are both writing into my cart. So let's say that event A is add a book to my shopping cart. So I'll just replace this letter A here. I was thinking about like, trying to draw a little picture of a book, but I'm not much of an artist, so you'll just have to contend. And then let's say C2 is adding something else to my shopping cart. So let's say I buy a pair of pants. Oh, let's actually draw the pants. There we go. Thank you, thank you. All right, so by the way, somebody in this class, Peter tweeted a photo of somebody's gorgeous sketch notes that they've been doing, and I don't know who that person is, but your work is beautiful, and I admire you as an artist, and I would love to see your rendition of the pants later on. Anyway, so now that I've replaced A with the book and B with the pants, all I've really done is, this is just a relabeling of A to book and B to pants, but does this give us any insight into what we can do to solve this problem? Yeah.
You don't need to do anything to solve this problem because the events are associative in a sense, right?
So I think the word that you meant to say was commutative, but yes, yeah, I think you're exactly right. So in other words, what we can do here is this cart that we're talking about, we can think of it as just being a set. And we can think of these things that we're writing into it as just elements of the set. And what do we do when a new element arrives? We add it to the set using set union. So if R1 is our cart here, and the book arrives, okay, now we have, here's our set, and it contains the book. And then the pants arrive, so now we have book and pants. And then on the other side, first we get the pants, and then we get the book. So here's our set. Okay, so what do we know about this and this?
They're equal.
They're the same set. So in some sense our problem is solved. And we know that our problem is solved because we know something now about the contents of A and B. Had A and B been something else that wasn't commutative, then we wouldn't be able to do this. But because we're looking at this problem in an application-specific way, and we actually know what A and B are, and we're looking at their contents, now we can see that these two rights are commutative. And so not only have we solved that, but we actually get some additional stuff out of this too. What if one of these messages gets lost? What if this message gets lost here? So what if that gets lost? And now I just have the empty set here. And I just have the set with the pants in it here. Now what can I do?
Take the union of R2 and
You
R1.
can synchronize them by just forming a union.
Yeah, so now R1 can say to R2, hey, what are your contents? And R2 can say, oh, well, I have these pants in this book. And R1 can say, okay, I'll take the set union of that and this, and it'll be fine. Now we get this book over here. What if R1 dies entirely? What if this whole process goes away? Then we still have R2, and then maybe some R3 over here will pop up, and then R3 is an empty state to begin with. But R3 can just ask, hey, R2, what are your contents? I'm going to union them together with the empty set that I have, and then we can get a message from here. So this commutativity that we know now that we can have, because we know that the content And in the limit, it's okay if, one of our replicas just dies entirely. So that worked for adding these items to the shopping cart. But what's the general principle behind this? What can we do in general? Does anybody have any ideas about what you need to have be true to be able to do this in general?
It's, well, in very simple terms, the fact that even though you might receive hands first and then a book, you get one set, and even though you might get a book first and then hands, it's the same set. And breaking this back to hashes, it's the same idea that you can compute the hash of a hash in any order, and it's going to be the same hash.
Okay. Yeah, go ahead.
You can't reduce the set. You can't take away from it.
Can you elaborate on that a little bit?
Well, yeah. So addition and subtraction are commutative with each other. Addition is commutative with itself, or set union, and never mind.
Actually, I think I see where you're going with this.
Yeah.
So later on, we're going to talk about what happens when you try to remove items from your cart. And your comment will become relevant. Yeah, go ahead.
You can't care about the order that things are added to sets, because once you do, then you have the issue of what was added first.
Yeah, so it's that commutativity that we were talking about. Okay, so
She was looking for something new.
let's talk about what it's going to take to be able to do this in general. And to do that, we need a little bit of math, but conveniently for me, most of it is math that has already been talked about in this course. But we'll review it again anyway. So what is a partially ordered set? Anyone?
Anti-symmetry.
Okay, so let's start. So what's the definition? So a partially ordered set is some kind of set, right? It's a set together with what?
Order and relations.
A relation, a binary, let's say a binary relation, some binary relation. What are the properties of this binary relation?
Transitivity.
All right. Let's start with this.
Reflexivity, the
Okay,
first one.
reflexivity. All right. What's the reflexivity property? What does it say? So if I have some element A, then A is, let's pronounce this as less than or equal. A is less than or equal to A for all A in the set. Okay, so that's the reflexivity property. Antisymmetry, what does that say?
A is less than or equal to B, B is not less than or equal to A. Or less than.
Unless B is equal to A.
So another way to say that is if A is less than or equal to B, and B is less than or equal to A, then what?
B equals A.
Right. All right, what's the last one?
Transitivity.
Okay, what does transitivity say?
If A less than or equal to B and B less than or equal to C, then A less than or equal to C.
All right, this is all review so far, right? Because we talked about this in the context of Lamport and so on. So these are the three axioms for that order that we have in a partially ordered set. What's an example of a partially ordered set? Anybody?
A is less than B. A is less than or equal to B.
Natural numbers, all right. Yeah, so the natural numbers, depending on whether you think they start with 0 or 1. So you get an order that looks something like this. So the usual ordering on the natural numbers is just this less than or equal to ordering. So the partial order would be like this. So is it reflexive? Yes. 3 is less than or equal to 3, for example. Is it anti-symmetric? Yeah, because the only things in there where you can say A is less than or equal to B and B is also less than or equal to A, the only things in there are those things that are themselves, right? So it is anti-symmetric. What about transitivity? Yeah, if 3 is less than 4 and 4 is less than 1 million, then 3 is less than 1 million. Yeah, so this is great. It's a good example of a partial order. Does anybody have any more interesting examples? Yeah, go ahead.
The vector blocks, right?
Vector clocks, okay. Does anybody have an example that's less interesting than vector clocks, but more interesting than natural? Yeah, good.
That's with the subset relation.
Subsets, yeah. So this is a really good example. So the subsets of the set. So if we think about our pants in our book, for instance, so the bottom thing in our, in our order is the empty set, right? And what's bigger than that? Well, the set that just has the book. Or the set that just has the pants. What's the relationship between these?
Not comparable.
They're not comparable, right? But we could have the set that has both of them, and that's bigger than both. And we could also add other things. So if I added another item to my cart, what else am I buying?
Cereal.
Cereal, all right. So, how do I draw a cereal box? Like this? All right. Okay, so then the set that has both the pants and the cereal is going to be a superset of those. All right. And we could also have the set that has the book and the cereal. And then way up here, we're going to have the superset of all of them. Okay, so it's not the most beautiful picture, but this is a great example of a partial order. So the order in this case is so P, my coset is, here's like, I could write this all out. It's the set of all subsets of this. So it's like the empty set, and then the set with the book, and then etc. I won't write them all. And then the ordering here is just the set including. So that's my partial order. So this, we could talk about how this respects the properties. But I think it's actually pretty self-evident. Okay, so that's all review so far. Now let's talk about something new that hasn't been covered in class yet. So let's talk about upper bounds. So using this as an example here, so we could pick out any two elements from our set of all subsets here. And remember, the elements of this partial order are themselves sets. So when I say we're picking out two elements, I don't mean pick out the pants or pick out the book. I mean pick out the set containing the book or pick out the set containing the pants. And we can ask which elements of this are at least as big as both of those two, according to our set inclusion order. So if I pick the book, the set containing the book, and the set containing the pants, which elements of this order are at least as big as both of those? Can you say it a little louder?
The set containing the book and pants, and the set containing all three.
Right, so this one is an upper bound of those two. And this one is also an upper bound of those two. Okay, what if I pick the empty set and the set containing the pants? What is an upper bound? What are the upper bounds of those two?
Any set containing the pants?
Right, this is an upper bound. What else is an upper bound?
All of the other sets of chance.
Right, yeah, so everything else up here, those are all upper bounds.
That one is not bad.
They're not looking necessarily.
Not, right, oh, sorry, yeah.
No, the
No,
other one.
no,
That's not right now.
up to the left.
Not this one, okay.
Both the cereal.
It's hard for me to tell, like, my box of cereal looks like a book, so. So, yeah, okay, so, in general, if we look at any two elements in a partial order, they could have multiple upper bounds. So, what's the definition of an upper bound formally? So, let's say given partial order, what's the definition of an upper bound? Yeah, go ahead.
It must be in the set S and greater than or equal to all of the elements.
Yeah, so say if we have two particular elements of S, A and B, so we'll say an upper bound. An upper bound of A and B is what? It's some element of that set.
And A is less than equal to the C, and B is less than equal to C.
C,
Or is it upper bound? Yeah, sorry.
C, such that A is less than or equal to C, and B is less than or equal to C? Is that what you said?
Mm-hmm.
All right. Yeah, that looks right to me. Let's call it U to stand for upper bound. Yeah, so that's what an upper bound is. What upper bounds are the ones that are interesting to us? Lowest upper bound.
The ultimate upper bound, like the biggest upper bound of everything in the set.
Well, that one's interesting in some ways, right? Because we know that it's the upper bound of everything. So somebody over here is the lowest upper bound. In what way is the lowest upper bound interesting?
Well, I'm thinking of it in terms of like big organization, how like, you know, everything's like an upper bound, but this is kind of a much better upper bound because we know it's at least as small as this in that sense.
Yeah, so yeah, I would argue that if you wanted to find the upper bound of two elements here, like this one and this one, well, yeah, I mean, you can say that that's the upper bound, but that's also going to be the upper bound of any two things that you pick out in this set. So in some ways, that's not so interesting. In a way, the really interesting upper bound is the smallest upper bound that's still an upper bound. Yeah, go ahead.
Because that's what the state would be if you did like a replication or it's a union.
Yeah, so
That's what you want.
if you think again about that picture that we were talking about earlier, when you were trying to figure out what's going to be the state that we should end up with when we have these two replicas that disagree, yeah, we're going to get back to that. So, yeah, so this least upper bound is what it's called. The least upper bound of the two elements is in some sense the most interesting upper bound. So, what's the least upper bound of empty set and the set containing the pants? Set containing the pants, right. What's the least upper bound of the set containing the pants and the set containing the book? Right, right. So the least upper bound is going to be the smallest upper bound that's still an upper bound. So we can write that down formally. Let's try to define it.
Question.
Yeah, go ahead.
Do all of the set of the upper bounds have to actually have an order? So if you given two elements, you compute all of their upper bounds. Do those upper bounds have to be ordered by themselves as well, or only in respect to the two elements?
Oh, that's an interesting question. Does anybody know? Anybody who knows more order theory?
'Cause that would,
The question is, if you have a bunch of different upper bounds, is there always going to be an ordering on the upper bounds?
there should be.
I think the answer is yes. So I know that, so there's not necessarily always going to be a least upper bound, right? But if there is one, it's unique. And I don't have time to go into why, but if there is a least upper bound, then there's going to be only one least upper bound. So let's try to write down what the definition of a least upper bound is. I'm actually going to cheat and look at my notes here. Let's see. So a least upper bound is a particular kind of upper bound, right? So we'll say an upper bound U, say upper bound U is the upper bound of A and B that belong to S. It's the least upper bound
No elements in A and B is known.
or lub for short, or it's sometimes also called the join. If what? When is it the least upper bound?
Less than every other upper bound.
Yeah, so if U is less than, according to the order, V for every upper bound, V of A and B. So that's the definition of a least upper bound, assuming U and V both also belong to S. So in this partial order that we're looking at here, do every two elements have a least upper bound?
Yeah.
Yeah, they do. In this one, they do. What about the natural numbers? Do every two elements there have a least upper bound?
No.
I'm hearing no and yes. Does somebody want to give an argument why it's either true or not true? Yeah.
Maximum of the elements is the least upper bound.
I should have said yes.
Yeah, so this is a really boring partial order, right? Because it's actually a total order. Yeah, so in a total order, you always do have that property that every two elements have a least upper bound. So not every partial order is going to have that property. Not every partial order is going to have this property that every two elements have a lub or a least upper bound. But in fact, there's a particular name for partial orders that do have that property. Does anybody know what that's called when you have a partial order where every two elements have a least upper bound? Yeah. It's almost a lattice. So you're close. So if you have a partial order where every two elements have a least upper bound is called a joint semilattice.
So you say COSET there, is that partial order set?
That's right, yeah. Yeah. POSET